So yeah, let's continue on the Fourier series, on the real Fourier series, as opposed to the complex Fourier series. But before we do that, I'm going to make one sidestep and talk a little bit about orthogonal functions and about a couple of trig functions. That having that out of the way will make talking about these things a little bit easier. First, let's talk about orthogonal functions. And if you want to read about that a little bit more, you can find that in the first appendix of chapter 5. An orthogonal function is defined as follows. We have a function of two variables, n and m. And the only condition when that thing is not 0 is if n is m. If and only if. Therefore the if with two f's. So that function basically evaluates always to 0 except when n is equal to m. And we're going to look at a couple of examples. You call it, by the way, orthonormal if the non-zero value is equal to 1. So if it's equal to 1, it's called orthonormal. We are dealing here with orthogonal ones, so I'm not going to talk about that much further. One example of such an orthogonal function that we will deal with a lot is this one. It's the product of cos nx with cos mx integrated over one full period. So that's what this t means. The period of the cos without with n or m being 1 is t, and the integration is over that period. And this is an orthogonal function, as we will see. But before we will see that, let's look at a couple of basics. If you would look, for instance, at this trig function, or this one, any idea what that would be, outcome of this integral?
0.
Yeah, 0. It's pretty easy to see, because if you assume n being 1, you can see that over one full period of this wave, now the period is basically here, you can see that the area under the curve here and there cancel. So that means that if you have an integral of a sine wave over a full period, the integral evaluates to 0 because the area on the curve is 0. If I make multiple periods, doesn't matter, they still cancel out. As long as I keep integrating over a full period. That's the trick. And that actually is the deeper reason why the Fourier, real Fourier series works so well for periodic functions, because you integrate stuff over a full period, as you will see. And when you do that, a lot of functions evaluate to 0. If we now, I know that you all know these functions, because we're going to use them quite a bit. And you have also one of the product for two cos functions. And then last but not least, a mixed one. I'm sure you all recall these functions from your trig lessons. Isn't it? And so now let's go back to our orthogonal function here, because now we are going to apply these trig functions to rewrite this expression. So now by combining this and that, I can rewrite this integral as the integral over a full period, 1/2 cos n minus m plus cos n plus m. Is that? And that's basically where I wanted to go. I didn't want to have this product, but I wanted to have this this expression with two terms. And now you can see that if n is not equal to m, in that particular case, I will have some kind of a cosine here and a cosine there with some integer value that is being evaluated over a full period t. So that means that in that case the integral part of the first term will evaluate to 0 and the integral part of the second term will evaluate to 0. I should put it like that. Now if n equals m, situation is a bit different, because now if n equals m, then still this component, the second term, will evaluate to 0, isn't it? That's kind of a number of oscillations over t. But the first one will be cos 0, and cos 0 is always 1, isn't it? So in that case, I will get, as a result, where this equals 1 always. So that will evaluate to, if I evaluate that integral, it will become capital T over 2. See, so here you have an example of an orthogonal function, the product of two cos functions evaluated over the fundamental period t, and is basically 0 when n is not equal to m, and is non-zero when n is equal to m, so that satisfies the condition for an orthogonal function. And if you made notes, kind of highlight this thing, because in a few minutes we will use this result. I now erase the result, but you wrote it down probably, so you will recall it, or be able to recall it. So now let's kind of go back to the real Fourier series. And in a way, the real Fourier series is just a mathematical expression of what we saw in this MATLAB routine, where we had a square wave, periodic square wave, and we tried to approximate that square wave with a bunch of sine waves. That's what we actually did. And that's, in a way, what the real Fourier series is trying to do. Let's say that we have some kind of a function ft, which is periodic, and we want to approximate that one, or represent that one, because as you will see later, it is actually pretty precise, and it can be shown that it is precise. And we want to approximate that one by a constant. That's the constant value. That's sometimes also called direct current or DC component of the signal. And just for practical reasons, you will see that in a little bit, most textbooks will put here the value of 1/2. It really doesn't matter, of course, because A0 is a constant, and if I just make that half of a constant, that's still fine. I am writing this a bit wide on purpose, but you don't have to do that. Then there is the next coefficient, and this is the, let's say, the base frequency, omega t. So we have a constant plus some sine wave, or in this case a cosine wave, plus a2 cosine omega, sorry, now. 2 omega t, so that is twice the frequency, plus etc. Of course, that you will get 3 omega t, 4 omega t, and you keep going. And then a little bit further, we have a coefficient b1 sine wave of omega t, plus b2 sine wave 2 omega t, plus, just like there, you can keep going until you are, in principle, until you are at infinity. And the more waves you include in your series, your Fourier series, the better your approximation is going to be. And the square wave we approximated with about 4 or 5 terms, and that was pretty good. But if I make more terms, which is one of your homework questions, you will see you'll get better in approximating it. So now the idea is that we have this function, which is a constant plus a bunch of cosine terms and plus a bunch of sine terms with all the frequencies present. And now we want to approximate, or maybe even represent, ft with pt. And we do that by selecting appropriately an and bn. Because you could see that also in our example, the amplitude of all the sine waves was not the same. The big sine wave had a large amplitude, and the smaller ones were associated with the faster oscillations. Now, how can we do that? A common way you do that in signal processing, and this is something you will see again and again, I'll do it again and again, but if you go in the literature, if you have a model and you have some measurement or some data set, basically what you do is say, well, I'm going to define some kind of an error, and that is going to be the difference between my series and the function that I want to approximate. And usually you do that over some period of time. Now the problem is, of course, that the difference can be positive and negative. and then it would cancel out. That's not what you want, because a negative difference is undesirable and a positive difference is also undesirable. So you solve that by just taking the square. See? So now you look at the differences, and you sum up all the differences over a full period. And since it is a periodic function, then I captured basically how well I'm fitting this time series. And now I'm going to minimize this error, and I do that by taking the derivative. And equating that thing to 0. That's kind of how to, if you think about your calculus class, that's the way of finding the extreme value. In this case, I'm actually not proving to you that it is a minimum, but it actually is. And also, so be aware here that I am taking the derivative, and I'm taking the partial derivative, hence this symbol here. I'm taking the derivative relative to the coefficients, see? So don't confuse this by taking the derivative relative to time, which is usually the case, or relative to x. No, I'm taking it relative to the coefficients because I want to select my coefficients in such a way that I minimize that function. So for that reason, it's the derivative to the coefficients. So what would that look like? Well, in that case, I would get now I will have to apply the chain rule. I have to take the derivative of this expression. So it is 2 times this expression, and then the derivative, in this case the partial derivative, this is what my condition is for coefficients A, isn't it? I took the derivative of this expression, 2 times this thing plus the derivative of this expression, applying the chain rule, and then that thing needs to kind of be equal to 0. And it's important here that I integrate over a full period again. So that's you will see in a little bit why that is important. That's because we are using these orthogonal functions. And that's the reason I was saying that, well, this real Fourier series likes to approximate things in a full period. There are a couple of things that I can do immediately. Since this is 2 times this thing is 0, so I can get rid of my 2, isn't it? If 2 times something is 0, then I can get rid of the 2. And the other thing that I can immediately see is that the derivative of ft to an is also not going to exist because ft does not contain any coefficient an. So this part can be forgotten as well.
Sorry, can you just repeat why that goes away?
Say it again?
Just repeat what you just said. Sorry.
Oh, what did I just say?
Why you can get rid of the ft there.
This one?
Yeah.
So ft is the function that you recorded, yeah, and that does not contain any coefficient a1. So that for that reason that will vanish. Okay?
Okay.
So this now becomes, and that's something I can easily do on the blackboard. This now becomes this, isn't it? Since that part vanishes. Let me get rid of this one too. So. Now we are not going to repeat this whole procedure for all an, but let's do just a0 and a1. So what is dpt, dA naught? I would agree with that. Yeah, I would say 1/2. Yeah, yeah. The result is 1/2 for A naught. We're talking about this expression now, huh? Now someone else, what will be the outcome for A1? Cosine omega t indeed, because if I do this relative to A1, vanishes. Here, yeah, there is A1, so cosine omega t will be the outcome. Here, this will vanish, this will vanish, this will vanish. So. Yeah? So what we established is that we can approximate ft with pt. In order to do that, we minimize that function. In order to minimize that function, we have to put that expression over there on the blackboard equal to 0. One part of that expression is the partial derivative of pt to an. And the partial derivatives for A naught and A1 are relative 1/2 and cos omega t. And of course for A2 it would be cos 2 omega t. And if I derived it relative to B1, it would be sine omega t, etc., etc. So that's a pretty easy thing to establish. Now let's see what would be the outcome of looking into a knot. In that case, that particular expression would become 1/2, which is the outcome of my A naught, integral pt minus ft dt is 0. Correct? So I just took that expression and plugged in 1/2. And since 1/2 is not a function of t, I put 1/2 in front of the integral. And just as I just got rid of that 2 over there, I can get rid of that 1/2 immediately, because 1/2 of something is 0, then something must be 0. Huh? So now I can simplify this expression to this thing. And now we need to start thinking. Because what I want to do is find out what this expression is going to be. This is actually why I left a little bit extra room for that. So I want to compute what this is going to give me. And that's pretty simple. I just apply this operation to all the individual terms, isn't it? And again, ignore this open space. I'm going to use that later. See? So I'm just trying to establish what is the outcome of this integral. And I think it's pretty easy, because let's have a look. Let's skip the first term. Let's look at this term. This is an integral over a full period of something times a cos omega t. So that's going to be 0. Yeah, because I evaluate that thing over a full period. The area under the curve vanishes. This thing vanishes. This is 2 times omega t. What's going to happen with that one? 0. Yeah, 0. Going to vanish too. It's 2 periods, but they still cancel. This one. Gone. Yeah, this one. Also gone. So the only one that survives is this term. That one is not going to be 0. So I can rewrite this thing as t 1/2 a naught dt is ft dt. Now I think even if your calculus is a bit rusty, you realize that this is a constant, so that integral is very easy to determine. If we take it from 0 to t, because if I integrate over a full period, it doesn't really matter where I start. So I'm going to start at 0. I'll say, okay, 0 t. I'm going to take 1/2 a naught out of the integral dt. Is going to be equal to ft dt. Well, this thing will be capital T. It will be capital T minus 0, so that's capital T survives. And then with a little bit of algebra, I find that a naught is 2 over t ft dt. So that's what I get out of this. Now realize that the DC term in this series is 1/2 a naught. So 1/2 of this thing, which is 1 over t, this expression, is your DC component, isn't it? So considering that that is the DC component, are you surprised by the answer? Not so much, yeah? Because what it says is that, okay, my DC component is just the average of my function, because this is the expression for the average of my function over a period of t. And yeah, it makes sense that that is your DC component. The other component, by the way, is often indicated as the alternating current or the AC component. If you ever forget these terms, think about the pop group AC/DC and you will know what it was. Okay, so is that clear? Because then we're going to go to A1. For A1, we had said that the derivative was cos omega t, So now my expression for the error becomes, integrating over a full period, pt minus ft times cos omega t, which was that partial derivative, dt has to be 0. And again, just as I did it over there, I'm going to rewrite this in two components. We have pt correct? So now we are going to do the same thing we did for A naught. We are going to look at our function here, and I'll look at this. I should have left a little more space there. So now I'm just evaluating, again, this expression here, just as I evaluated this expression there. Well, this was our friend, isn't it? This one. So let's start with the first term. What's going to happen with the first term? That'll go, isn't it? It evaluates a cosine function over a full period. So that it's gone, vanishes. Then this one is the orthogonal function, isn't it? So that is going to be 0, except in this case. And then this is a sine-cosine product. And if you actually put in the trig there, you can do that at home. But I can tell you with confidence that these things also vanish. They're all gone. Because they always vanish. And a cosine sine, that's not even an orthogonal function. It's always 0. So in this case, the only term that survives is actually this one. So I now can write here outcome of this integral you still know, because I had you highlight that you in your notes about 10 minutes ago. That was t over 2 times a1 and if you, in this case, if you solve for a1, I'm going to write it here above a naught, you will get this thing. And you can apply this, this same trick repeatedly. And then you would find that in principle you would be able to replace this by an, and that you would have to inject an n here, which is really nice because that means that every coefficient is only depending on its own frequency. That's really a nice aspect of this real Fourier series. And by the way, if you did the same approach, and you can look that up in the textbook, if you do the same approach for B, then you get Bn is equal to this expression, and then the cos is replaced by a sin. And so also there, with the B coefficients, they're only depending on their own frequency. And so you can also determine them independently. So I can say in this case, oh, I have a series, I want to approximate this series. I'm just going to go up to 3 or 4 coefficients. And since all these coefficients are independent, it's really fine. I can just stop whenever I want. Whenever I feel that I approximated the whole thing sufficiently. Now the thing, and we'll get to that in a little bit as well, the thing that I did in this example that I showed you last time with program 5_1, where we approximated the square wave, I just computed, in this case, the coefficients for a number of iterations for a square wave, and just plugged that into a MATLAB code and approximated a square wave in that fashion. So I used this, this trick. This is the real Fourier series. So, any questions before we continue on that? No? Because now we are going to go to the complex one.
I think you have a question.
Okay.
Oh, quick question.
Yeah.
So if you stop at 2 coefficients,
Yeah.
and then you plug P of t into that error function, will that get you the error then?
Yes. Yeah, it will. Any other ones? Okay. So the only thing that we change here is that real will be replaced by complex. And if you want to read this again in the textbook, you can find this on page 81. A couple of things before we get started. Do recall that j squared is -1. I actually use j instead of I, so some textbooks will use I, some will use j. And another one that's important is the Euler relationship. If you have an exponential with a complex exponent, you can always represent this, if this is your real axis and this is your imaginary axis. You can always represent this thing on the unit circle. That's a circle with a radius of unity, where this is the phase angle phi, and then this will be your exponential with a complex exponent. And as you can see, that contains a real component which is proportional to the cosine of phi, and it contains an imaginary component that is related to the sine of phi. And that is exactly what this Euler relationship is telling you. And so these two relationships are relationships that we will use very often. Now, if you look at the complex Fourier series, this is the expression. Let me first show you what the expression looks like. So you might think that this looks very different from the real Fourier series. It is also a series of terms. In this case, they are terms with coefficients c instead of a and b. And then instead of cosines and sines, we have an exponential. And then just as we had an expression for determining a and b coefficients in the real series, we have an expression to determine the coefficients in this complex series as well, and this is the expression. Now you may be surprised, but this is just a different notation of exactly the same thing. So it's just a real Fourier series with a different notation, and we're going to look at that. Yes?
So just in terms of practical applications, like when would you use complex and when would you use real, and why do you need both?
Good question, and I have to ask you to be patient and bear with me a little bit.
Okay.
The complex Fourier series is going to lead to the Fourier transform, and the Fourier transform is actually very useful in analyzing data. That's the reason. So yeah, you will have to have about 1 to 2 lectures patience, and then we will start using it. So it's a fairly complex matter actually before we can get to the application. But it's a fair question. In order to show you that this thing is actually the same thing as the real series, we're going to rewrite this the series as follows. We're going to have C naught plus So the only thing I did here is that I separated this single summation term, and I now get 3 terms. The C naught term, where n is 0, and then the part that goes from 1 to infinity, and the part that goes from minus infinity to minus 1. So I basically cover the same area. I just rewrote it in 3 separate terms. And this thing I can actually rewrite again This is kind of a trick to sum over the same area as this. So instead of going from minus infinity to minus 1, I can now go from 1 to infinity, just as over there, and I just change the sign of n. So it's now c minus n, and the exponential is also negative. That actually is an indication how we get to a concept of negative frequencies. Because, what is a negative frequency? Well, it rolls out of the math here. Because, of course, I've never seen a negative frequency, neither have you. And then we're going to rewrite this thing, Cn, using our Euler friend here. And the only reason that I am writing it in this way is that I want to simplify the notation of Cn. And that's something you can do a lot. There will be an exam question and there's a homework question about that as well. You just say, well, you know, I really don't care what all this is. In the end, it is a complex number. And that complex number consists of a real part and an imaginary part. And just as that we did in the real Fourier series, for convenience, the convenience will appear later, we multiply that with a half. But that half has nothing, is not really essential. It's just convenient because the outcome will help. Now, to make this a little bit easier, I have to introduce you to another set of terms as a little sidestep, and that is the concept of odd and even symmetry. And you can read about that in Appendix 5.2. It's not that difficult actually. It's if you look at a cosine function around 0, you see that the positive values and the negative values mirror. So this value here is exactly the same as that value there, and that is called even symmetry. So a cosine has even symmetry. Whereas a sine wave, as you all know, that's not the case, because this value here is maybe in absolute sense the same as that value there, but the sign is opposite. And that is called odd symmetry. So that's the sine wave has odd symmetry. So this is even, that's odd. Why is this an easy thing to do? Because now we can evaluate a little bit easier what we mean by this C minus n. Because we know that Cn is this expression, isn't it? So based on this reasoning, what would C minus n be? Well, I would say that 1/2 doesn't really matter. The real component of this expression is cosine related, isn't it? So that means that I can write an is going to be exactly the same thing as Cn. However, the imaginary component of this expression is sine wave related. And that is related to an odd symmetry. So that would be, in this case then, plus JVM. For that reason it's, and we will use that more, this odd and even symmetry, it's just practical to deal with that. And a special case is C naught, which is the DC term. The DC term is 1/2 A naught. Why is B naught 0? Because the DC term is a real term, and it also has even symmetry. I mean, it's constant over time. So it doesn't have any odd component. And for that reason, you can, just by looking at it, you can already say, by knowing about odd and even symmetry, you can say, well, B naught is 0. Okay, now let's rewrite this thing. So now we had PT is 1/2 A naught, because C naught is basically 1/2 A naught, isn't it? Then we have n is 1 to infinity 1/2 A n minus j b n times, continue on the next line, cos n omega t plus j sine n omega t plus n is 1 to infinity 1/2 A plus JBN and then cos n omega t minus j sine n omega t. So the only thing I did is I rewrote now the Cn as the coefficients, and I rewrote the exponentials also using Euler as cos and sine waves. So again, I just rewrote this expression, and now it's in this form. Now there's a lot of algebra involved now, but what you basically need to do is you just expand this everything, you multiply everything, and then you select and collect all the terms, and you do all your additions and subtractions, and then on page 83 you can find all that algebra. I'll try to show it for the camera here. So that's what you do. You just multiply everything, collect all the terms, make all the things that cancel, etc., vanish, and then lo and behold, your end result looks like this. pt is 1/2 a naught plus the sum of which is, as you will recognize, exactly the expression we had for the real Fourier series. So you see, with a little bit of algebra, we came from the complex Fourier series, where you had complex coefficients and complex exponentials. You just kind of worked it all out. It is just a different way of presenting the real series. So to that extent, to answer your question, when would you use what? In a way, it doesn't matter. It's just a different notation. Let's do one example, a more or less theoretical example, so it's not talking about sampled time series yet, but just to give you some feeling about the analysis. Let's look at the example on pages, 86, 87. And that is, that involves this is the axis. This is time, and this is amplitude. And this amplitude is A, and this amplitude is minus A. And this is our friend, the square wave. We have seen in that example in the MATLAB approximation. And this would be its fundamental period. And now the question is, how can we approximate that with a real Fourier series, which is actually the analysis I did to write program 5_1, because I just did not guess these values. I just knew what these values were, and this is how I knew. Well, first of all, it's a periodic square wave. And I can see that there is no DC component, isn't it? Because this thing fluctuates around 0. So I don't have to do anything. I can already see that my A0 is going to be 0. The second thing that I can see, that this is an odd wave form. Well, if this is an odd waveform, I don't need cosine terms. So that means that all my AN is 0. You see, by just looking at it, you can already get rid of a lot of things you don't need to do. And then the third thing is that we will now use equation 518 for establishing Bn, because since we have odd symmetry, of course, these terms do not all vanish. And what we will do is we will use that equation 518 for Bn, but we will split it in two pieces. That is because over the one period I basically have two pieces of my waveform. I have a piece that is plus A, and I have a piece that's minus A. And so it's practical to split that. So if I then apply that equation, see? So I have to multiply the function with the sine wave and then integrate over the full period and multiply it by 2 over t. That's what the equation tells me. But since my function is discontinuous, I'll just take each continuous part. That's actually one of the advantages of the Fourier series, that you can represent discontinuities in your function. If you just have polynomials, of course, that's a lot more difficult. Well, if we rewrite this a little bit, we get this thing. I just took the a's out of the equation, they're constants. And then I can evaluate these integrals. So this is the integration of this sine wave is this expression. If you don't believe me, you can differentiate it and you will see that you'll get this thing. And then we have to evaluate that from 0 to t over 2. And of course for this one we get the same expression. So I'm going to write it as that. The only difference is we have to evaluate it from t over 2 to t. So this expression is exactly the same as that expression. So now we're almost there. If we now plug these outcome or these evaluations in and we rearrange the terms a little bit, plus we are using also this equation that omega is nothing else than 2 pi times the frequency. And the frequency is just 1 over t. So we're going to rearrange the terms and plug that in for omega. And then we will get That's what will come out of this. Now that's an interesting equation. Just recall that the cosine will look like this, isn't it? If this is pi, 2 pi, 3 pi, etc. And this is 0. It will look like that. So the cos of 0 is always going to be 1, of course. A cosine of 2 pi something will always be 1 as well. Because it's either 0, 2 pi, 4 pi, etc. It's always going to be 1. The only guys that are a bit more difficult to evaluate is the pi ends, because when n is odd, the outcome is -1, and when n is even, the outcome is +1. So that means that this expression that we get here for our bn's are different for odd and even ends. If n is odd, we will get bn is 4a divided by n pi, and if n is even, these terms cancel. So again, kind of 1 minus 1 minus 1 minus 1, and that's 0. That cancels. In the other case, it's 1 minus minus 1 minus minus 1. And then you get 4. So now let's, just for the fun of it, go back to the example we started with as an introduction. And here you see the square wave, and you see the sine waves with different amplitudes. And if you look at the frequency component here, you can indeed see that only the odd versions for n are non-zero, and you can also see that the first term is indeed 4 times. It says in this case 4 over pi, because I took a as being 1, so it's 4 over pi for the first one, and the next one is of course 4/3 over pi, etc., etc. And as a matter of fact, if you open up your function, I can quickly do that. Yeah, so if you open up the function for program 5_1, you can actually see that the first part, the first component here is setting the stage, the time, the base frequency, etc., etc. But then the part that where I used my knowledge about this time series, which was based on the calculation we just did on the blackboard, you can see that here for S3, S5, S7, S9, and then the total, which is the sum of all these contributions, you can see that indeed I do here 4 pi times 1/3, 4 pi times 1/5, 4 pi times 1/7, etc. And now you, since you now know these equations, you can easily add terms, which is one of your homework questions. And then, if you do it right, you should get a somewhat better result. Although this one wasn't bad, it can be better. Good. Any questions before we stop? No? Okay, then we're done.